All right, so we are going to look at optical devices today that are mirrors. And we all use a mirror at some point in our life. Sometimes we use them every morning. Sometimes we avoid using them every morning. But nevertheless, we all have experience with mirrors. And we're going to look at 3 different types of mirrors in a very conceptual way to begin with. And then later videos will highlight details about the properties of those 3 types of mirrors. So, the types of mirrors we're going to be thinking about are the plane mirror, a concave mirror, and a convex mirror. Now that word concave and convex we also use when we described lenses. And if you recall in our discussion of lenses, those were physical definitions, what the actual mirror looks like. But our lenses also had operational definitions. And so as we explore these 3 types of mirrors, we'll also introduce the operational definition. Now, mirrors work on the principle of reflection, the law of reflection. And there's a whole little mini lecture on the law of reflection. So I'm just going to recap it super quick. You can look at that mini lecture if you choose. The law of reflection tells us that the angle of incidence of a light ray hitting a reflective surface, so something that's going to bounce that light back, is equal to the angle of reflection. And so it looks very symmetric, and we kind of use that example of playing pool or billiards, right? Where if I hit, when I'm strategic in my playing of billiards, I try to hit at the angle I want the ball to bounce off at. Well, the same is true, that's our analogy for our law of reflection. Now, there were a couple really important key pieces of that, and that's going to come into play when we look at our curved mirrors. And that is that angle is relative to the normal. Okay, so that idea of the perpendicular plane at that point of incidence where that light ray hits the surface. Okay, so plane mirrors. Plane mirrors are flat. They're perfectly flat. All right, so if we think of a plane mirror, we think of the type we see in our bathroom window, our bathroom wall, or our clothes mirror in a clothing shop to check out our new outfits. So plane mirrors have that totally flat, and the law of reflection is pretty intuitive when we think of light in a plane mirror. So the light ray comes in, incidence on that plane mirror, and that light ray bounces off such that the angle of incidence is the same as the angle of reflection. Now, if I were to look at parallel rays of light, so I'm going to use a different color. So if there was another ray of light that came in, oops, parallel, that doesn't look very parallel. So we have another ray of light coming in at the same angle. It will bounce off. Parallel. So parallel rays of light on a plane mirror bounce off parallel. All right. So, and that's sort of the introduction. We'll talk about image formation in each of these mirrors in separate mini lectures. But parallel rays of light come in to a plane mirror and bounce off parallel. Okay. What about a concave mirror? So, concave, just like it is with lenses, is that shape inward in a lens. And a concave mirror, we only look at one side of that mirror. Why? Well, because that light's not on the other side of the mirror. So light doesn't pass through, it bounces off. So here's our concave mirror. Now the law of reflection still applies. So let's bring in a ray of light. We're going to add a little bit more definition in here. This, again, if I bisect the mirror at the middle, this we're going to call our optical axis again. And as we move into image formation with these mirrors, we'll talk about light rays being parallel to the optical axis. So I want you to be familiar with that terminology. All right, so parallel to the optical axis, we'll use that. That's the horizontal ones, the ones I can draw really easily. So here is a parallel ray of light. Let's kind of come in and hit the mirror. Now, if we think about the law of reflection, just like with my lenses, I have to draw that tangent to the surface. There's my tangent to the surface at the point of incidence. I then look at my normal to that tangent. And the angle of reflection is equal to the angle of incidence relative to the normal. So it's this big of an angle is going to give me my angle of reflection. So my light ray bounces off. All right? Okay, we see that the ray of light at the top is sort of reflected down here towards the bottom. What about light rays that come in the bottom? Oh, I won't use pink. Oh, funny. I put it on the wrong cap. All right, so we'll bring a parallel ray of light into the bottom here. Choo-choo. And I do the same thing where I look at my point or my tangent. My normal. And I sort of look at that angle. And my little steep there. I'm going to get a straight edge. I'm really not doing good with these lights, these edges. And my angle of reflection is equal to that angle of incidence. All right. Now what do we notice? Well, light rays that come into the bottom, they're all going to be directed towards the top. And light rays that come into the top are all going to be directed towards the bottom. They are going to come together or converge. So, for a mirror, a concave shaped lens operationally converges the light rays. That's different than the lenses. Remember, the lens, a concave lens, was a diverging lens. But for mirrors, a concave mirror is a converging optical device. And we can see that through the law of reflection. These light rays all come together to a common point, and every parallel ray of light will be reflected through that point. It's a property of the mirror. Now, what's going to affect this point? Well, first let's define what that point is. As you might expect, this is called the focal point. All right, so the point at which the light rays come together. And similar to our lens, the distance between the focal point and the lens and the mirror, is the focal length. Now, what is going to dictate that focal point? With a lens, it depended on two things, right? It depended on the curvature, was one of them. How about the curvature in a mirror? If I were to make this curvier, this very same ray of light on a curvier surface, well, the tangent would be steeper as I'm drawing it, and therefore the light ray would be brought sharper down earlier. So as I increase the curve, I decrease the focal point and the focal length. I bring it down sooner. If I make the curve more shallow, the focal length increases. So as I make that curve shallower, I decrease the curviness of the mirror. the focal length increases. What is this curviness related to? And actually, we can now begin to even be more careful with what this focal point is related to. So that curviness is one. The other thing that dictated where that focal point was for a lens was the material it was in. Remember, we looked at the air versus the glass. But if we put it in water versus glass, well, now the difference in the two mediums is less, and the amount of refraction would therefore be less, and the focal length would change. It's the same true with a mirror. Well, the law of reflection is not dependent on what the light ray is in, because it's not changing the rate at which that light ray is traveling by being more optically dense. And so it doesn't matter what we're in. If we put this in water, the light ray that comes in at this angle theta is going to be reflected at that angle theta, whether it's in water or whether it's in air. So the medium does not matter in the case of mirrors. Only the curvature of the mirror, only the curvature of the mirror. And we can use our ideas about tangent lines and steepnesses and that following with that law of reflection to get these ideas. So the focal point is defined by the curvature. If I think about this mirror as a piece taken from a sphere, so imagine a sphere, and I've just taken a piece of this sphere out and plopped it here, and the inside surface is reflective. This focal point is actually related to something about this sphere. This sphere has a certain radius. The focal point is 1/2 the radius of that sphere. Now, we call that radius something special. We call this radius the radius of curvature. And we use the capital letter C in optics to define that. So the focal point is 1/2 the radius of curvature. And that's going to be important as we look at image formation in this type of mirror. All right, so concave mirrors converge the light. Their focal point, how they converge that light, in terms of where all those parallel rays of light would in fact cross the optical axis at the same location, converged, is related to the curvature and specifically related as 1/2 the radius of the sphere that mirror would have come from. Okay, so that's a concave mirror. I bet you can imagine that the convex mirror is going to be similar in some capacity. So, operationally, what does a convex mirror do? Well, if the concave mirror converges, I'm going to guess that you can deduce that the convex mirror would do the opposite, and you would be right. So our convex mirror is what we know as a diverging mirror. So let's look at how that happens using our law of reflection. All right, so convex means it bows out. So that's if we took this sphere and instead of the reflective surface being on the inside, it was on the outside. So there is a concave vex. I get them good. I say them too quick. A convex mirror where the reflective surface is on this side. All right, so let me draw an optical axis. And let's look at how a ray of light enters the convex mirror. So again, I'll use my parallel ray of light, my horizontal as I've drawn it, to the optical axis. Well, we follow that same principle. We draw our tangent line. We make our normal relative to the tangent, and our reflected ray is at the same angle relative to to the normal. So we see a ray coming in is reflected in the upward direction. What about a ray that enters the bottom of the mirror as I've drawn it? Well, follow that same process. Look at our tangent line. We draw our normal to that tangent. And we have a ray reflected. Oh, that was a little big. Downward. So we can see, and if I have more parallel rays of light, they're all going to be reflected away from each other. Not only that, but let me draw a parallel ray of light at the top, another one, so parallel to the incoming ray. But this ray of light, and of course I'm freehanding these angles so they're not perfect. Put my normal. These rays of light are not parallel. We can see that they are getting wider and wider and wider apart. So even parallel rays that come in and are both reflected in the upward direction relative to how I've drawn it are going to spread out because they don't reflect parallel like they do in a plane lens. And so all rays of light are reflected away from each other. They diverge. But this looks strikingly similar to our circle before. So there's going to be something about how these images, how the shape of the lens plays a role relative to, again, that radius of curvature. So if I make this a curvier mirror, the light rays are going to be reflected even further apart, similar to the other mirror. So as I increase the curviness, I get more divergence. If I decrease the curviness, I get less divergence. They're still going to diverge. They're still going to diverge. So what is it related to? Well, it relates to that curviness. And how is that curviness defined? It's defined by the radius of the circle. So a convex mirror also has a focal point and a radius of curvature. The radius of curvature being the radius of that circle that sphere came from, and the focal point being half that. So same rules apply. Now, pictorially, and when we do image formation, we will do this very carefully. But to give you a preview, where that focal point and radius curvature is related to if the reflected rays, we'll see how good my drawing is, if the reflected rays went through the mirror. Didn't do such a great job. That's not bad. I'm going to fix this. That looks too tight, doesn't it? Yes, I think so. If the reflected rays went through the mirror, they would converge. That one's not too bad. I'm cheating a little bit here because I did not do that very well. You can see that would, yeah. They will converge at a common point. A common point being the focal point. And as previously discussed with concave mirrors, that's half the radius of curvature. So you can literally imagine this being taken out of the sphere and plopped there. That is going to be important as we look at image formation in the lens, in the mirror, excuse me. That focal point on the inside is going to be important. All right, so conceptually, these ideas of optical devices that are mirrors, the law of reflection applies. With a plane mirror, parallel rays of light are reflected parallel. With a concave mirror, it converges light rays as it comes into the mirror to a parallel rays are converged to a common point. We'll see how image formation is made with that convergence. And a convex the light rays are diverged, and again we will see how image formation occurs with the divergence of those rays. All right, good job.